Hi friends, good morning to one and all. This is my second lecture on mission drawing subject, and today's topic is conventional representation of engineering materials and mission components. In this session, I will explain how to represent or how to draw the conventional drawings for engineering materials and mechanical mission components. Okay, conventional representation. Certain drafting conventions are used to represent materials in section and mission elements in engineering drawings. This is the conventional representation of engineering materials, as a variety of materials are used for mission components in engineering applications. It is preferable to have different conventions of section lining to differentiate between various materials. The recommended conventions in use are shown in figure. Okay, these are the some examples for conventional representation of engineering materials. For how to represent metals, how to represent metals. For example, steel, cast iron, copper, lead, zinc, tin metals. How to represent a conventional representation. This is a plate. Okay, right. I consider a rectangular plate. Now I am representing the metals like this by drawing hatching 45 degrees angle lines. Wait, these are the hatchings. Hatchings are used for representing the sectional views as well as metal surfaces. Okay, these hatching lines are parallel to each other, and I consider the angle of inclination with the normal lines is 45 degrees. Okay, so this type of representation is used for steel materials, steel metals, cast iron, copper and its alloys, aluminum and its alloys. Okay, now, if lead, zinc, tin, white metals are there, how to represent that metals? I will show you. Here also I consider a rectangular plate. Here also I am drawing the hatching lines, same 45 degrees angle inclination with the normal lines. Okay, but what is the difference between this one and this one? So for showing the variation, I am drawing the double hatching in opposite hatching lines. These hatching lines are also 45 degrees inclined to the normal lines. Okay, these are the double hatching lines. Okay, okay. These double hatching lines is used for lead materials, zinc, tin, white metals like this. Okay, so this type of conventional representation is used for metals. Okay, this is single hatching, this is double hatching. Now another example. Now I am showing the conventional representation for packing and insulating materials. How to represent for packing and insulating materials? This one and this one both are packing and insulating materials. But here the examples are given for porcelain, stoneware, marble, slate like this. How to represent for these materials? Okay. Here also I consider a rectangular plate. Okay, rectangular shape object. Okay, For packing and insulating materials, you have to represent dashed lines, same dashed with hatching. Okay, these are discontinuous lines. Okay, these are also having 45 degrees angle with the normal lines. Okay, so this type of representation is used for porcelain materials, stoneware materials, marble materials, and slate like that. Okay. Now, if you want to draw the conventional representation for asbestos materials, fiber materials, felt, synthetic resins, paper, cork, linoleum, rubber, leather, wax, insulating and filling materials, how to represent for these materials? Yeah, for these materials, I am drawing the horizontal hatching lines. These are the horizontal lines. So now, uh, for indicating packing and insulating materials, I am drawing again dashed lines. Sorry, continuous lines with 45 degrees angle. Okay, okay. This is the example for packing and insulating material. Okay, now coming to the real life application for glass, how to represent conventional representation of a glass material. How to represent for glass material? I will show you. This is here also I consider a rectangular shaped glass. Okay, for clear indication, I am drawing small lines like this. Okay, okay. I am repeating same. Okay, now here also I am repeating same procedure. Okay, this is the these hatching lines. These hatching lines are used to represent the glass materials. Okay, this type of representation is used for glass type materials. Okay, now how to represent the how to represent for liquid materials, for example water, oil, petrol, kerosene, like this, like these these fluids, how to represent for these liquids. Here also I consider a rectangular container. Okay, now for liquids I am drawing the dashed lines, but here I am drawing horizontal dash discontinuous lines. Okay, okay, this is the example for liquid materials. Okay, so this type of convention is used for water, oil, petrol, kerosene, like that liquid materials. Okay, now how to represent for wood, plywood materials. For wood materials, you have to represent like this or like this or like this. Okay, you can represent any one of these three. Okay, this is the conventional representation of a wood material. Okay, now I am showing how to represent for concrete materials. Concrete is a mixture of already we all of you know that concrete is a mixture of cement, sand and gravel. So you have to represent cement, sand and gravel materials. Okay, so here also I consider a rectangular shaped slab. Okay, so in this first I consider I am showing the a mixture of gravel. Okay, These are the some particles. These particles represents gravel. Okay, now I am adding a cement. Okay, cement and sand. Okay, these small dots represents cement and sand. Okay, this is the example for concrete materials. Okay, concrete is a mixture of gravel, cement and sand. Okay, this is the conventional representation of a concrete. Now, how to represent for mechanical mission components. Conventional representation of mission components. So here, when the drawing of a component in its true projection involves a lot of time, its convention may be used to represent the actual component. Following figures shows typical examples of conventional representation of various mission components used in engineering drawing and machine drawing. Okay, so this figure, uh, represents straight knurling. This middle part showing straight knurling. These straight lines indicates straight knurling. Okay, now this one and this one represents diamond knurling. This is the example for diamond knurling. This one also diamond knurling. This one also diamond knurling. Okay, here this is there is no knurling on this surface. This is a straight knurling. This is a cross knurling. These are the diamond knurlings. Okay, how to represent this type of knurlings? Okay, how to draw the conventional representation of straight knurling and diamond knurling. Okay, in next slide I will show you how to represent for straight knurling and diamond knurling. Okay, so please once again remember this is straight lines indicates straight knurling. These crossed lines indicates diamond knurling. Okay, okay, I will show you for straight knurling. This one is a straight knurling on a shaft. This is the conventional representation of a straight knurling. For this, I am drawing first. I am drawing this wheel. Okay. Then after I am drawing this shaft. This is the axis. This is the axis of a shaft. Okay. Now, in real time, these all straight lines you have to draw. But for saving time, there is no need to represent all these lines. Just you have to draw 3 or 4 lines for conventional representation. For conventional representation, just you have to draw 3 or 4 lines on shaft. Okay, this type of indication represents straight knurling on this wheel. Okay, this is the example for straight knurling. This is the conventional representation. This is the actual representation. Okay, diamond knurling. How to represent diamond knurling? This is the actual shape of a object, but our convenient for a convenient how to represent this diamond knurling. Here also I am drawing this wheel first, the axis, and this is the shaft. Okay, how to represent these diamond lines? For representing these diamond lines, I am drawing crossed lines, that is the hatching lines. Okay, these are the left hand hatching lines. Then after I am drawing the right hand hatching lines. Okay, these intersecting lines produce diamond shape. Okay, so these are showing diamond shape. So these are the example for diamond knurling. This above figure represents these straight lines represents straight knurling. Okay, this is the main difference between straight knurling and diamond knurling. Now, this is the example for square on shaft. This circular line represents shaft. This square, this is square position represents square on shaft. Okay, how to represent this diagram? Now this is the holes on circular pitch. Circular pitch means the distance between two successive holes is same. Okay, here the distance between these successive two holes is circular pitch. In real time, how to represent these holes on circular pitch and square on shaft? I will show you. First, square on shaft. This is the original diagram. Okay, this is the shaft, square shaft. Okay, how to represent this square shaft? In real, this is the real time diagram, but in machine drawing, I am showing a conventional view like this. Okay, this is the square. This is the square on shaft. So this cross lines represents square on shaft. Okay, this is the example for square on shaft. Now holes on circular pitch. How to represent holes on circular pitch? This is the plate, circular plate. Now this dotted line, this dotted circle represents circular pitch. Circular pitch, pitch of a circle. Okay. I Now I am dividing this circle into 12 parts. Okay. Now I am drawing circles at the intersecting point. Okay. This one is sixth circle. This is a seventh circle. This is a eighth circle, ninth circle, 10, 11th circle, and this one is 12th circle. So in real time, uh, for drawing all these circles, it takes many time. Okay, for saving our time, we are representing a conventional view. Okay, so for saving a time, I am showing a conventional representation. Okay, this outside circle like this same. Now I am considering inside a circle, dotted circle, same dimensions. There is no change. Then after I am dividing the circle into same 12 equal parts. Okay, there is no change here. Now I am showing only one circle on this circle, on this figure. Okay, there is no need to represent all circles on this figure because this conventional representation indicates all circles on intersecting points. Okay, this is the conventional representation of a holes on circular pitch. Okay, each circle maintaining equal space, that is circular pitch. The distance between two successive circles is called circular pitch. Okay, now these are the examples for threads. Okay, this one is external threading. Okay, this one is example for bolt. Okay, hexagonal bolt. This hexagonal bolt having external thread. Okay, this is also external thread. Okay, this is not a bolt, this is a shaft. Okay, threads on shaft. Now this one is a internal threads on shafts. Okay, now this one also example for internal threads. Here, what is the main difference between external threads and internal threads? Here, in external screw threads, the threads are appears on outside of the shaft. Okay, here also threads are appearing on outside of the shaft, but in external screw threads, threads are not visible to outside. Okay, how to represent for external screw threads and internal screw threads? I will show you external screw threads. Okay, this is the example for external screw thread. This is the actual diagram. But for drawing this actual diagram, it takes many time. It takes more time to complete the figure. So to minimize the time, okay, to reduce the loss of time, I will show the shortcut method to represent the external threads. Okay, this circle indicates outer diameter of a thread. Okay, this is the outer diameter of a thread. Okay, this circle indicates outer diameter of a thread. Okay, this is the front view, that is the shaft. Front view of a this thread. Okay, it shows like a rectangle. Okay, this shaft shows like a rectangle. Now this middle rectangle shows this rectangle. Okay, now for drawing these threads, I will represent by a straight line. Okay, by representing like this, it shows threads on shaft. That is the external threads. Okay, but in side view, we have to represent the external thread, external screw thread symbol. We have to mention, or you have to draw the external screw thread symbol. For that symbol, you have to draw a incomplete circle. Okay, this incomplete circle shows the thread. Okay, this in here you have to draw internal circle. Okay, this incomplete circle you have to draw inside of the circle. Okay, this incomplete circle shows external screw thread. Okay, this incomplete circle shows external screw thread. Okay, this is the conventional representation of a external screw thread. Okay, there is no need to draw all these thread lines. Okay, there is no need to draw all these lines. This is the best and easy way to represent the threads. Okay, in our machine drawing we are having so many problems on these threads. So in all these diagrams we are representing like this. Okay, this is the axis of the thread. Okay, now how to represent the for internal screw threads. Okay, this is the hole. Inside the shaft there is a threading. Okay, by using tapping instruments you can make threads. Okay, how to represent these internal threads? Here also I am drawing this box as a front view. So this outside diameter of a hole, I am drawing this outer diameter of a thread. This circle represents outer diameter of a thread. So this height equal to this height. Okay, same height I am drawing the rectangle box for representing the threads, for representing internal threads. Okay, for internal threads you have to represent threads like this. These horizontal lines represents threads. Here also this horizontal lines represents threads, depth of threads. Okay, here also this line represents depth of threads. Now I am showing this sharp corners. Okay, these are the groove. This one is a groove. At the time of boring or drilling, it may visible. This is the axis of the shaft. Okay, now here for internal threads you have to draw a incomplete circle. Okay, here I am drawing the circle outside of the thread, outside of the complete circle. Okay, this incomplete circle shows internal screw thread. In above figure I am drawing the incomplete circle inside the circle, but here I am drawing the incomplete circle outside the circle. This is the main difference between internal thread and external thread. Okay, these hatching lines represents cutting section. Okay, now this shaft shows splined shafts. Okay, these are shows splined ends. Okay, here splines on shaft. These spline shafts are using in gearbox. Okay, now this one is bearing on shaft. This one is bearing. This is a thread, external thread. This one is bearing. Okay, this one is a ball bearing. This one is shaft. This one is threading. Okay, how to represent bearing on shaft and how to represent spline shafts, I will show you in next slide. First one, bearing on shaft. This one is the actual figure. This is the shaft. Okay, this is the bearing. Here I am showing the sectional view of the bearing. Okay, this is the ball bearing. This small circle represents balls, so this bearing is called ball bearing. Here instead of this ball I am drawing a rectangle. This rectangle shows rollers, so this bearing is called roller bearing. Whatever it may be, how to represent bearing on shaft, here I will show how to represent bearing on shaft. First you have to draw this shape, that is a shaft. First you have to draw a shaft. This is the main shaft for mounting the bearing. Okay, for easy representation I am drawing a small rectangle box, then after I am drawing diagonal lines. Same I am repeating here also. So these two rectangle box with crossed lines represents bearing on shaft. Okay, this is the convention representation of a bearing on shaft. Now I am showing splined shafts. How to represent splined shafts? This is the front view of a splined shaft. Okay, how to represent this splines? These two lines I am drawing like this, diameter lines. Then after you have to draw just 2 or 3 splines. Just you have to draw 3 or 2 splines. Then after you have to draw like this dotted circle. there is no need to draw all teeth. These are called, these springs are called teeth. Okay, there is no need to draw all teeth on circle. It may take much more time to draw all teeth. Okay, to reduce our time, we are showing like this. Okay, this dotted circle represents continuous teeth on this circle. Now, how to represent interrupted views? Okay, this is a solid long shaft. Okay, in real applications, it is very difficult to draw a 400 or 300 rod on drawing sheet. It is very difficult to show that dimension on drawing sheet. For that purpose, I am drawing like this. This is the example for interrupted views. Okay. Okay. Actually, for example, the length of this shaft is the length of a shaft is 500 So it is very difficult to show this 500 on drawing sheet. Okay. So to overcome this problem, I am showing like this, but I am marking the I am showing the dimension like this, but I am showing the same dimension. Okay, there is no need to draw all the length. Okay, total length. There is no need to show total length of the shaft. By showing like this, okay, by showing like this, we can reduce the shape of the diagram. Okay. Similarly, interrupted views for hollow long shaft. This is the hollow shaft. Okay, this circle indicates solid shaft. This double circles indicates hollow shaft. Okay, how to represent for interrupted views for hollow shaft? Here also same purpose. For very long shafts, I am showing like this. Same diagram, but the difference between this one and this one is here. This I shape here, I am drawing the hatching lines for solid shafts, but hollow shafts don't draw the hatchings because this one is hollow. Okay, just draw another arc. Okay, this double arc indicates hollow shaft. Okay, now these are the examples for leaf semi-elliptical leaf spring. Okay, this one is elliptical spring. This is the application of a leaf spring in automobiles. Okay, in real life we can see, we can observe so many places. This is the example of a leaf spring. Okay, this one also semi-elliptical leaf spring. Okay, how to represent these leaf springs? This one is leaf spring without eye. This one is leaf spring with eye. These circular shape, are called eyes. Okay, this one is without eye. This one is with eye. How to represent this leaf spring and this leaf spring? I'm showing. semi-elliptical leaf spring without eye. This one is the original shape of a leaf spring. In our drawing purpose, I am drawing just two arcs like this. Okay, this figure indicates semi-elliptic leaf spring without eye. Okay, now how to represent semi-elliptic leaf spring with eyes? These both are eyes. How to represent these eyes on this leaf spring? This is the original diagram. Okay, I am drawing two arcs same as above. Okay, so at the end of arcs you have to draw two small circles. These small circles indicates eyes. Okay, this is the conventional representation of a semi-elliptic leaf spring with eye. This one is without eye. Okay. Now these are the examples for mechanical springs. This one is an example for cylindrical compression spring. Okay, this type of springs uh, carries only compressive loads. Okay, these cylindrical compression springs carries only compressive loads. Okay, now this one is the example for cylindrical tension spring. These tension springs carries only tensile loads. Okay, these springs also used in many automobile industries. Okay, these springs are used for absorbing the shocks. Okay, how to represent this cylindrical compression spring and cylindrical tension spring? Cylindrical compression spring. This is the actual diagram. This is the actual diagram, but for saving our time, I am drawing like this. Okay, these inclined lines represents these inclined lines. Then after you have to join these inclined lines also. For that purpose, I am drawing inclined lines like this. So this is the complete shape of a spring. Okay, this is the line diagram for springs. Okay, this is the conventional representation of a compression spring. For in compression springs, there is a gap between two successive turns. Okay, this is the axis of the spring. Okay, now how to represent cylindrical tension spring? This is the actual diagram, but for saving our time, I am drawing in a simple way. Okay, now I am drawing this arc for carrying the tensile loads. Okay, this I represents hook. These hooks useful to carry tensile loads. Now coming to the bearings. How to represent spur gear? This is the actual diagram. Actually, this spur gear contains many teeth. Many teeth on hub. This one is the hub. Okay, this hub contains teeth. Okay, these are called teeth. How to represent this spur gear? Now I am showing conventional representation of this spur gear. Okay, this is the side view. This side view I am showing. Okay, this side view contains a hole. This one is a hole, and these here it is very difficult to draw all teeth on drawing. So for saving our time, we are showing just a circle. Okay, this dotted circle represents teeth, depth of the teeth. Okay, this hole represents this hole. Okay, this slot is used for key. Okay, now this is the example for spur gear. Now I am showing bevel gear. How to represent bevel gear? This is the actual diagram of a bevel gear. How to represent this bevel gear? Here in spur gears, the teeth are in straight, but bevel gears, the teeth are in inclined shape. Okay, how to draw these inclined teeth? Okay, this one is the front view. Okay, this one is the this side view. Okay, okay, this is the example for bevel gears. Now, how to represent worm gears and worm wheels? Worm and worm wheel. Now, this one is worm. Worm. This shaft represents worm. Okay. Now, this bottom wheel represents worm wheel. Okay. How to represent worm and worm wheel? So, for this worm, just you have to draw a shaft. Okay, then after this this line and this line represents depth of the thread. Okay, this worm shaft contains threads. Okay, so this depth of the thread indicates by this line. Okay, this is the side view of the worm. Okay, now this is the figure for this worm wheel. This worm wheel having small curve on the top of the teeth. Okay, so this is the diagram for worm wheel. Okay, here I am showing with more example. Okay, you can observe here this worm wheel contains curved cutting edges at the top of the teeth. Okay, so these are the examples for gears. Okay, in next class I will explain more diagrams on threads. Okay, okay, thank you.